In this video, we are going to revise Organic Chemistry 1 and 2. We will be using past topical questions to do the revision. But before we continue with our topic today, I want to thank those of you who have taken your time to subscribe to my channel. For those of you who haven't subscribed to this channel, please like this video, share to other learners, and most importantly, take some time to subscribe to my channel. Thank you for taking some time to subscribe to my channel. Let's get started. We will be starting with question number 1. Question number 1 has to do with polymerization, and specifically on condensation polymers. So molecule A and B can form condensation polymers. You see the structure of the molecule A. Molecule A is a diol. Molecule A is a diol. It has two OH groups. Molecule B is a dicarboxylic acid. It has two carboxylic acid groups attached to the molecule. Now, for the purpose of revision, what is a condensation reaction? A condensation reaction is a reaction in which two molecules join together, and a simple molecule such as water is removed at the same time. Esterification is an example of a condensation reaction. Condensation polymers are formed from monomers with two functional groups. A simple molecule such as water is always eliminated in a condensation reaction. Example of functional groups involved in a condensation reaction are the OH group, which we have just seen there, a COOH group, that is the acid group, which is still there. There is also an NH2 group, that is an amine group. Polyesters and polyamides are examples of condensation polymers. During a condensation polymerization, a polyester is being formed. When a molecule of water has been released, a polyester is being formed. A polyamide is also being formed. Somebody might ask, what are polyesters? Polyesters can be made from dicarboxylic acid. Polyesters can be made from dicarboxylic acids. As I earlier said, a dicarboxylic acid, that is molecule with two COOH group, two carboxylic acid group attached to it. And a diol, that is a molecule with two OH group also attached to it. So, getting back to our question, each molecule has two identical functional groups. Name the functional group in B. The functional group in B is what? Is a dicarboxylic acid. A dicarboxylic acid. The functional group there is a dicarboxylic acid. Or you can call it a carboxylic acid. The functional group here is a carboxylic acid. Or if you want to call the two, you can say a dicarboxylic acid. The examiner will accept the two. Question number 2. Draw the part of the structure of the synthetic polymer that would form when two molecules of A, that is a diol, and the two molecules of B, that is a dicarboxylic acid, combine together as I discussed in my introduction, I said when these two they meet, a polyester is being formed. So they are asking us to draw the part of the structure of the synthetic polymer. Let me just call it a repeated unit. Draw the part of the repeated unit. The repeat unit in this when two of these and two of these they meet. Okay, take for example, this is the structure here. As I said, this is a diol, and this is a dicarboxylic acid. Okay, in a dicarboxylic acid, it is a COOH group. It could be written, the bonds could be written out like this. Dash C, a double bond O, a double bond O, double bond O, and a bond to OH group. You could easily write them like this so that you can see how the water is being eliminated. Okay, now, when two molecules of A and two molecules of B, they meet, what will be the reaction? Look at it very well. Okay, this is a dicarboxylic acid. I told you that the bonds can be written out like this. These are the bonds that are being written out. The COOH is written out in this form. So in that case, let me write it. Okay, B, which is a dicarboxylic acid, this is how the bonds are written. A C, double bond O, and then a bond to OH. Then again, on this other side, a C, double bond O, and a bond to OH. Then, and a diol. A diol is the two OH group attached on both ends. Now, then another B again. B is a carboxylic acid group. The bonds are well written out. Another carboxylic acid group, the bonds are written out. Then later, molecule A again, that is a diol, also written there. Let me show you how the electrons, how the molecule of water is being eliminated, since it's a condensation reaction. When this OH of the dicarboxylic acid combine with the hydrogen of one of the hydrogen of a diol, okay, a molecule of water is being formed. It is being eliminated. Then a bond is formed between the C double bond O and the oxygen. This is the bond here. This is the bond here between the C the double bond O and the oxygen. This is the bond here. And this bond is what we call the ester linkage. This is an ester linkage. When an acid reacts with an alcohol, an ester is being formed. So this is an ester that is being formed. But there are many of these esters that are formed. That is what we call the polyesters. So the link between the acid group and the alcohol group is what we call the ester linkage. So now one of the hydrogen of the OH combined with the other OH group of the carboxylic acid will eliminate a molecule of water. It continues like that. The OH of the carboxylic acid with one of the with one of the hydrogen of the diol, and a molecule of water is released. Again, if the reaction is going to continue, there will be an OH or an OH from the acid here that will combine with the other. When an OH of the acid comes here, it will also combine with the hydrogen of the diol, and a molecule of water will be released just like that, like that. The bond continues. So they have limited us only to two molecules of A and two molecules of B. So a molecule of water is being released here, and this bond is being formed. This is the bond that is being formed. This is an ester linkage bond. This total bond here is what we call an ester linkage bond. Now we come here. This is the same bond. When this one is formed here, this is an ester linkage bond here because a molecule of water has been released. Then forming and this bond linking this carbon double bond O and the oxygen of the alcohol or the OH. So now it's an ester linkage bond that is here. The same thing will occur here where a molecule of water is formed or where a molecule of water comes from. That is where an ester linkage bond is being formed. Now, the same thing happens here. You will see here that the OH bond of the carboxylic acid and the hydrogen of the diol, when they meet, a molecule of water is being eliminated, and that is where the ester linkage bond is being formed. This C double bond O and the C single bond O, that is what we call the ester linkage bond. So now, if we are actually represent a structure, a part of this molecule, because this molecule here, this molecule that I've just written like this molecule, it gives what? This molecule this molecule, as you see it like this molecule here, when these molecules of water are removed, it will result in this. It will result in this polyester. This is the polyester beginning from here. This is the polyester beginning from here, coming here, and ending here, plus 3 molecules of water that have been released from this. And now, from this polyester, we are asked to present a repeat unit or a section of the bond that has been formed. This will be it. Between one carboxylic acid, this one is from a diol, this one here, this is the one of these molecule that is being linked with this one. So we will now represent this structure. This structure here will represent what we call part of the structure of pyrroline. That is the repeat unit. Then there will be the ester linkage bond. And if we are asked to represent it in our answers, if you are asked to represent this in your answer, this is what you are supposed to write. This is what you are supposed to write. Let's go back to our question paper. This is what you are supposed to extract there and write. This will be, as I told you, this is from the carboxylic acid and this is from the diol. So from here, a molecule of water was being released. And this is where an ester linkage bond is being formed. And that's why I say as this is part of the structure of pyrroline. This is a repeat unit of it. So draw part of the structure of the synthetic polymer that will form when 2 molecules of A and B combine. So this is part of it. This is part of it. So this is part of it. If you look carefully, this is part of it, and this is the rest of it. This other section is the rest of it. So that is how you are supposed to write. And if you did like that, you have 3 marks. Name the other product formed when molecule A and B undergo polymerization. You see the other molecule, name the other product. As I said in the equation, this is the equation. We had 3 molecules of water that were being released. So the other molecule or the other product that was formed is water. Okay, molecule A is a simple sugar. Let's say molecule A is a simple sugar unit, which can be made by hydrolysis of complex carbohydrate. Draw part of the complex carbohydrate that could be hydrolyzed. Part of it that could be hydrolyzed. Draw part of the complex carbohydrate that could be hydrolyzed to make molecule of A. Molecule A, if you look at it critically, molecule A is a diol. It's a diol. It has 2 OH group there. So if we were to hydrolyze, this is a complex molecule that we were to hydrolyze. If we hydrolyze this by using acid hydrolysis or enzyme hydrolysis, we are going to break it from here. And if we break it from here, this is what is going to form. Or if we break it from here, this is what the structure is going to be. If we break from here, this is how the structure is going to look like. So this is draw part of a complex. This is a complex carbohydrate. Okay. Now, state 2 sets of conditions. State 2 sets of conditions which could be used to hydrolyze the complex carbohydrate. Okay, carbohydrate to form molecule A. To hydrolyze a carbohydrate like this one, a carbohydrate is a sugar molecule that can be hydrolyzed. There are 2 ways. Either you use what we call acid hydrolysis For example, you can use hydrochloric acid, or you can use enzyme hydrolysis. An enzyme which is like amylase. For example, in the mouth, in the saliva in the mouth, we will have amylase. Amylase in saliva will break down starch. In your mouth, when you have some carbohydrate, there is an enzyme that we call amylase. The amylase is found in the saliva in your mouth. It will break down starch into maltose. No, that maltose is a disaccharide. It's a disaccharide that is made up of two glucose units. So there are two, either an enzyme hydrolysis or an acid hydrolysis. Then number 3, name the technique used to identify the individual sugar units made by the hydrolysis of a complex carbohydrate. The only technique today that is used is what we call the chromatography. Chromatography is the only technique that is used to identify the individual sugar units made up by the hydrolysis of a complex carbohydrate. Okay, the C part. Ethanol can be made from the simple sugar glucose. Ethanol can be made from the simple sugar glucose. That is, ethanol is alcohol. It can be made from simple sugar glucose. Any substance that has glucose in it. It could be locally produced wine, anything that has glucose in it. Alcohol can be produced from it. State the name of this process, the process in which ethanol can be made from simple sugar glucose. The simple process that is well known is what we call fermentation. When you ferment a glucose, after a period of time, ethanol is being produced. And maybe in order to have a pure ethanol, to separate the pure ethanol from the water during the fermentation, it has to be taken to a unit where there is distillation, in a distillation chamber where they will be boiling, and because of the difference in the boiling point, ethanol will evaporate and enter into a condenser that is now finally drip into a container that is being collected there. Okay, so we will say it is fermentation. It is fermentation that is used for this process. Complete the chemical equation for this reaction. Okay, ethanol is broken down. Glucose is broken down into ethanol, and the carbon dioxide is always another product that is being produced. So we can balance the equation by putting a 2 on carbon dioxide and 2 in front of ethanol. That is the only way you can balance this equation. Okay, question number 2. 2A. Propane reacts with chlorine in a photochemical reaction as shown. This is propane plus chlorine to give chloropropane. That is chloropropane plus hydrogen chloride. What type of reaction is this? Halogens, when they react with alkanes, it is going to be on a substitution reaction, provided it is going to be a substitution reaction, provided there is sunlight or there is a UV light. So in this case, the type of reaction here is substitution reaction. Then 2, what condition is needed for the photochemical reaction to occur? For photochemical, just from the word photochemical, it needs light. Photochemical, it means that this is a light required reaction. A light required reaction. So light is needed, and in this case, that is UV light, or what we call UV radiation. Now, draw two structural isomers of compounds with the formula C3H7Cl. Of course, we have just 2 structural isomers, and they say show all the atoms and all of the bonds. Show all of the atoms and all of the bonds. So writing out the bonds clearly, you will see that we will have 2 chloropropane and chloropropane, or what we call 1 chloropropane. We are to use the IUPAC system of nomenclature. It will be 2 chloropropane and 1 chloropropane. Now, propene reacts with chlorine in an addition reaction as shown. Propene is an alkene. It reacts with chlorine in this way. State why this is an addition reaction. It is an addition reaction because the compound is an alkene. It is an addition reaction because the compound is an alkene. Or it is an addition reaction because it has a double bond. The compound has a double bond. There is addition across the double bond. So you can say it is addition reaction because it is an alkene, or because the compound has a double bond. You can say because the compound has a double bond. That alternative you can put so because the presence of a double bond. You can put it there, or presence of a double bond. It's an alkene, or presence of a double bond. Compound has double bond. You can say compound has a double bond. It's acceptable. Writing the word alkene is a double bond. Compound has double bond. Compound has a double bond. So you can write because the compound is an alkene, or compound has a double bond. It's acceptable. Okay, the structures of the reactant and the product of this reaction are shown. These are the structures of we have one okay, prop 1 in, and we also have chlorine here to form 1,2-dichloropropane. 1,2-dichloropropane. Now, in this case, some bonds energies are shown in the table. We have the carbon-carbon bond, which is 347. We have the carbon-carbon double bond, which is 612. We have the carbon hydrogen bond, which is 413. We have the carbon-chlorine bond, which is 339. We have the chlorine bond, which is 247. The question reads, calculate the energy change for the reaction between propene and the chlorine using the following steps. Now, the steps have been given. The steps calculate the energy needed to break bonds. Energy needed to break bonds, usually it is an endothermic reaction. So energy is absorbed from the surrounding to break bonds, and it is usually endothermic. So now, and it has a positive value. So in that case, let's look to break bonds. Energy is needed to break bonds. Energy needed to break bonds. Breaking of bonds takes place but in reactants. Breaking of bond takes place in reactants. So in that case, let's look at the number of bonds here. The carbon-hydrogen bonds. How many carbon-hydrogen bonds are here? We have 1, 2, 3, 4, 5, 6, 6. There are 6 carbon-hydrogen bonds there. Now, let's go to carbon-carbon single bond. The carbon-carbon single bond in this occasion is, we have just 1 here. For reactants, to break bond, breaking of bond takes place only in reactants. Products are not involved. So we have only 1 carbon-carbon single bond. Now, carbon-carbon double bond, we have only 1 of it. Now, going to chlorine bond, we have only 1 chlorine bond. So now, substituting the values that have been given here for the carbon CH bond, a carbon hydrogen bond. The carbon hydrogen bond is 413. When we substitute here, it will be 643 plus only 1 CH bond, which is substituted, only one carbon double bond which is substituted, and only one chlorine bond which is substituted. If we multiply this, 6 times 4 13 plus 343 plus 612 plus 242, our total value will be 3,678 kilojoule. Now, that is energy for the breaking of bonds. Now, energy for the formation of bonds, or energy release when bonds are formed, this is exothermic. Now, we need to look, and that takes place only in products. Now, bonds are formed only in products. So let's go to the product section. We have for the carbon hydrogen single bond, we have 1, 2, 3, 4, 5, 6. So carbon hydrogen bond, we have 6. We have 6 there. For again, in the products, the carbon a single bond. Carbon single bond have 1 and 2. So we have 2 there. A carbon single bond, that is 2. Now carbon chlorine bond. In the product we have carbon chlorine, which is 1, carbon chlorine, which is 2. So there are 2 of them there. So these 2, now we substitute the values. When we substitute the values here, 6 times 4 13 plus 2 times 339 plus 2 times 347. When we add all these values, we will have 3,850 kilojoules. Now, to have the energy change, calculate the energy change for the reaction. There is a formula we call enthalpy change for the reaction, or energy change for the reaction will be summation of energy for bonds broken, that is this one, minus summation of energy for bonds formed, that is the second one. So now, if we substitute our enthalpy of reaction, or energy of reaction, energy change for the reaction, for bonds broken, it will be 3,679, minus for bonds formed, it will be 3,850. When we do this subtraction, our difference for that is energy change will be negative, that is minus 171 kilojoule per mole, and that will be our answer. If you did that, you have 3 marks. Now, the C part of it is there are 3 functional groups in compound A. Of course, in compound A that we did the other time, there are 3 functional groups in compound A. This is compound A here, of course. That is compound A. The functional groups they are there. The first functional group is the alkene group. That is the double bond. That is alkene. The second functional group is the carboxylic acid. That is the COOH. Then the third functional group is the alcohol. That is the OH. That is the OH group. So there are 3 functional groups that are involved in it. Name the homologous series of compounds that contain the following groups. Name the homologous series that contain the following groups. Okay, now the double bond is the alkane. The OH group is the alcohol, or in some other book you can call it alkanols. Then the COOH is what we call the carboxylic acid group. Functional group, once more, for functional group, let me come back there again. What is a homologous series? What is a homologous series? A homologous series, these are compounds which have the same general formula. They have the same general formula, and each member will only differ from each other by a methylene group, that is a CH2 group. Another characteristic for homologous series is that these are compounds that have the same chemical properties. They have the same chemical properties because each member has the same functional group. Another characteristic that is unique of homologous series is that the physical properties, they show the same graduation. There is the same gradation in the physical properties. I mean that physical properties like melting point and the boiling point, they show a constant increase. For functional group, what is a functional group? A functional group is a group of atoms like the OH group that we have just seen, like the COH group that we have just seen, like the C double bond C that we have just seen, as a group of atoms that all members of a homologous series have in common. Let's get back to our question. What would you observe when compound A, this is compound A here, what would you observe when compound A is added to aqueous bromine? Aqueous bromine. Remember that aqueous bromine is always used for the test for the presence of aqueous bromine and alkene. Aqueous bromine and alkene are always is used for the test of the presence of alkene. Only alkene can react with aqueous bromine. So what would you observe when compound A is added to aqueous bromine? We are not going to use the alcohol group. We are not going to use the carboxylic acid group, the COH group, but the other functional group that we are going to use here is the carbon, is the alkene group, is the C double bond C. So our observation, aqueous bromine, bromine water is decolorized. Only alkene will decolorize bromine water. Only alkene, homologous series with a carbon-carbon double bond. Only alkene will decolorize bromine water. Alcohol will not do that. Carboxylic acid will not do that. So we'll only use alkene. Only alkene is very reactive in this case. We'll give an indication of that. So we'll now say with aqueous bromine, bromine water is decolorized, or bromine water becomes colorless. Aqueous sodium carbonate, if we add aqueous sodium carbonate here, if we add aqueous sodium carbonate here, what will be observed is that, remember that when an aqueous sodium carbonate is added with an acid, when a carbonate reacts with an acid, carbon dioxide is being produced as a gas. And when carbon dioxide is being released as a gas, what we will observe in the laboratory will be effervescence. Bubbles of gas are being released. Fizzing is observed. So in our answer, what you will write will be effervescence, or fizzing, or bubble of gas. So with carbonates, when carbonate react with acid, a gas known as carbon dioxide is always released. And that is observed from the bubbles of gas that are coming out from the test tube, or fizzing that is being observed, or effervescence. So any of the words, effervescence, fizzing, or bubbles of gas, is acceptable. They mean one and the same thing. Okay, D part of it. Compound A can be used as a single monomer to produce two different polymers. One, draw one repeat unit of the addition polymer from, draw one repeat unit of the addition polymer formed from compound A. Addition polymer. Addition reaction will only occur with alkenes. So addition polymer, what will happen with addition polymer is just that when we add to produce a polymer of this, when we add other units of this, what will happen will be that the double bond will, this double bond will get off, and there will be another bond here. There will be another bond here. There will be another bond here, and there will be another bond here. So that is how, then there will be no, so there will only one single bond here, and there will be another one here, another one here. All the units will be added like that, added like that, added like that. for when it has to do with addition polymerization. When it has to do with addition polymerization. Let me clear it off. Okay. When it has to do with addition polymerization. So now they are telling us draw one repeat unit of the addition polymer formed from A. In that case, this is how I told you that the double bond will disappear. It will only be a single bond. So this will be a repeat unit of this. This will be at the repeat unit. Okay, what type of condensation polymer is formed from compound A? A condensation polymer that is formed from compound A, if there's going to be a condensation polymerization, a condensation polymer that is formed from here. Remember, a compound A is what? It has an acid group in it, and it also has an alcohol. So when an acid reacts with an alcohol, what is going to form will be an ester. And if it's a repeat unit, if it's a polymer that is being formed, many ester groups are going to be formed. So there are going to be ester linkages that are going to be formed in it, resulting in what we call a polyester. So because acid group is involved and an alcohol group is involved, a polyester is going to be the product. So the type of condensation polymer, the polymer is formed from this will be a polyester because of the COA group and this. Okay. Question number 3. Methane, ethane, and ethene are hydrocarbons. Draw the structure of the molecule of ethane. Show all the atoms and all of the bonds. That is how ethane molecule is. Ethane is C2. It is C2H6. So this is the structure of ethane. That is a C2. That is C2H6. That is ethane. So this is the structure of ethane. Which one of C2? Okay, which one of these compounds belongs to the same homologous series as methane? Homologous series as methane. Methane is an alkane. As I told you that a homologous series, these are compounds that have the same general formula, the same chemical properties, then the physical properties show the same gradation. I just explained it to you. Now, which one of these compounds below belong to the same homologous series? So the homologous series is alkane. Methane belongs to alkane. And here, the only alkane here is not methanoic acid, is not methanol, and is not propene. So the only alkane here is butane. You circle it. C part of it. Ethene can be manufactured by cracking. Complete the sentence about cracking using words from the list. We have atoms, ions, larger molecules, reactive, and smaller. So cracking, what is cracking? Cracking is the process of breaking down larger alkane molecules into smaller alkanes and alkanes. So the word required there, breaking down, is larger. Alkanes molecules into smaller. So those are the three words: larger, molecules, and smaller. You have that, you have your 2 marks. State 2 conditions needed for cracking. The 2 conditions that are needed for cracking, cracking must take place at a very high temperatures. Or if you have a catalyst, for example, aluminum oxide, then no problem. So either high temperatures or using catalysts. Now, polyethylene, that is a polymer of ethene, is made by the polymerization of ethane. Which one of the structures represent part of a polyethylene molecule. Remember that when polyethylene is there, when there is polyethylene, it's made from ethene, and this is an ethene molecule. This is an ethene molecule. This is an ethane molecule which is here. If we have this, so now, uh, what is happening? Okay. In this case, I was ethene. This is an ethene molecule. This is an ethene molecule. So this ethene molecule, if this ethene molecule has to undergo what we call addition polymerization to form what we call polyethylene, what will happen will be that the double bond here will disappear. This will be the molecule of it. It will be the molecule. Yeah. If this polyethylene has to do many structures, this will be the structure of it. This will be the unit of the polyethylene. It will just be the unit. This will be the unit. There are many other ones because the double bond will disappear. So now, in this case, um, so in this case, here we will have the structure here. Which of the structure represent part of the polyethylene molecule? The structure here will be, it cannot be this one, it cannot be this one, it cannot be the one containing the OH group, it must only be this one. So nylon is also a polymer. Give one common use of nylon. Nylon is one common use of nylon is used for clothing. It's used for clothing. Is used for making fishing lines, or used for making fishing lines, or fishing nets, or ropes. Part of the structure of nylon is this one here. How many different types of atoms are shown in this structure? The atoms here we have hydrogen is 1, nitrogen is 2, carbon is 3, oxygen is 4. There are 4 different types of atoms that are there. The structure of a monomer used to make a polymer is shown below. What structural feature of this molecule shows that it is unsaturated? Unsaturation is indicated by a double bond or a triple bond. So what structural feature of this molecule shows that it is unsaturated? The only is the presence of the double bond. So we can carbon-carbon double bond, or what we call carbon-carbon double bond. can write it like that. Describe a test to show that this compound is unsaturated. The only way to identify the presence of unsaturation is using bromine water. The presence of a double bond is the use of bromine water. So we can say addition of bromine water into the above compound. On addition of bromine water into the above compound, what will be the observation? Bromine water is decolorized, or bromine water is decolorized, or it turns bromine water colorless. That's the observation. Bromine water is decolorized, or bromine water turns colorless. So that is a simple test for it. And that is it. Thank you for listening. We are very grateful for the time you have taken to listen to our lesson today. Once more, I want to thank those of you who have taken time to subscribe to our channel. And for those of you who haven't subscribed to the channel, please, in order to have subsequent revision lessons, subscribe to our channel, share this video with other learners, and like the video. Thank you.